Hello, my name is Steinar Eastwood. I'm from the Norwegian Meteorological Institute and I'll be talking about ice surface temperature activities at the Norwegian and Danish Meteorological Institutes. This presentation has been made together with Gorm Dybkjær at DMI. First, an overview. I'll show you the range of IST and SST products that DMI and Met Norway are involved in. I'll talk about our latest advances in IST retrieval, including cloud masking, temperature algorithms, and validation of IST. And I'll finish with showing some example of IST monitoring and climate perspective in the context of decay of polar sea ice extent. So, the range of IST-SST products that we're involved in. Both IST and SST are delivered to provide seamless surface temperature field in the area where there's sea ice. Here is shown an example over the Arctic. For near-real-time products, we produce the EUMETSAT OSI SAF level 2 and level 3 products based on AVHRR and VIIRS instruments. We are also involved in the definition of the level 2 and level 3 IST products from Sentinel-3 and the EUMETSAT responsibility. On the climate side, we are producing the ASTI climate data record, which includes also an interim climate data record. This is based on AVHRR GEC data, so it covers the period from 1982 until present. DMI is also involved in the level 3 and level 4 products in the Copernicus Marine Service. Now for cloud masking and the difference between cloud masking over sea and over ice. For SST retrieval, there's usually a good contrast both in the visible and infrared between the sea surface and clouds, while for the ice retrieval and the ice surface is similar as clouds in the visible brightness, and for infrared, its surface can even be colder than the overlying clouds, and hence the cloud masking is more challenging over ice, especially at night time. So we wanted to quantify this by looking at how good the cloud mask is and validate the cloud mask. The cloud mask software that we've been using is the PPS version 2021 from the EUMETSAT nowcasting stuff, which includes both a classical cloud mask and a cloud probability. We've been using the Calliope cloud lidar from the Calypso satellites to validate these cloud products. The Calliope instrument detects the presence of clouds and aerosols in the multiple levels. And here is an illustration that shows how the LiDAR detects the cloud top in nadir view. We have validated the cloud products for Sentinel-3 in the Sci4MaST project over the Arctic. The Calliope and the Calypso instrument is a Calypso satellite is now out of mission, but we are looking forward to the EarthCare mission that is being launched these days, so that this activity can continue. So I'll go straight for the validation results. This table shows the validation scores for both SLSTR, VIIRS, and AVHRR over polar regions, so including both ice and water. These are from different validation exercises, so are not directly comparable, but still they show what I want to illustrate, that at daytime we have the best results. If you look at the orange column, we show the false alarm ratio for clear, so the percentage of clouds that are falsely classified as clear and we want obviously this number to be low. For daytime, this is there are reasonably good results, while at nighttime we see that the percentage is as high as 40 and above, which illustrates the problems at nighttime with the quality of the cloud mask. We have also specifically validated the cloud probability product to see how the cloud probability can improve the cloud masking. This table shows the validation scores for SLSTR, and we have now separated sea ice and polar waters. We focus on the ice, the results over ice, since we have most validation data there. And we have binned results in cloud probability ranges. So the first line is for data over sea ice with the probability of clouds between 0 and 5%. The second line is over ice and for cloud probabilities between 6 and 10% and so on. And in the orange columns we see the false alarm ratio for clear again. And the lowest, the best performance is as expected for the lowest cloud probabilities with 10% false alarm ratio at daytime, and then increasing false alarm ratio with increasing cloud probabilities as expected. At nighttime, we now also see that the false alarm ratio increases with increasing cloud probability, but the validation results does not get better than 35% for the lowest cloud probabilities. So there is some skill in also at night to identify the best quality nighttime pixels, but probably the best use of these results is then to use the validation numbers to impact how the confidence or the quality levels are set for the IST retrieval, with different quality level at daytime and nighttime. Now for the IST algorithm, we are using a classical split window algorithm as shown here. Since IST covers a large range of temperatures, the algorithm was first set up with coefficients for 3 temperature intervals. So a set for cold temperatures, one for medium range temperatures, and one for warmer temperatures up to melting. Now we are planning to replace this with only one set of coefficients, since validation indicates that the one range algorithm performs as good as the 3 range algorithm. Over to validation of IST. For IST, it's difficult to get good in situ validation data from sea ice. We need observations of the skin temperature, as the sub-skin or snow temperature can be very different from the skin. So the situation is not similar as for sea surface, where you can use the sub-skin or depth temperature to validate the skin measured by the satellite. We have tested this by putting buoys on the ice, but they measure something which is either into the snow or into the air, and we will not know which temperature is measured, as these buoys are not, the snow conditions vary during the season. We have some campaigns where we are testing new instruments for estimating the skin temperature. The Svalbard Marginalized Zone campaign is a campaign to observe and better understand the complex interplay between atmosphere, waves and sea ice in the winter marginalized zone north of Svalbard. Observations during this campaign included an open met buoy setup with 4 thermistors, illustrated here in the figure on the top right. 1 thermistor at 1 meter, 1 at 10 centimeter, 1 thermistor on the lying on the snow surface, and a thermistor buried into the snow on the interface between snow and sea ice. 34 of these buoys were deployed on the ice floe from a Coast Guard ship. But before we went on this campaign, all thermistors were calibrated against a reference sensor. And as you can see on the right, we have the calibrated results, and on the left we have the uncalibrated results. And the calibrated results indicates that the accuracy of the calibrated thermistors are slightly below 0.0 degree, which is sufficient for our studies. The Svalbard region is a very dynamic region with ice breaking up and drifting. Some of the buoys did not stay long on the ice before they ended up in the water, but some buoys provided more than 1 month of data. And here we see the buoys that survived the first period and drifted along with the ice. It's a Sentinel-2 image, high resolution visible in the background, and then we see the trajectories of the different buoys on the ice. The next step is to collocate these observations with satellite IST products for validation, and I will come back to you with the results on a later occasion. So this activity is to be continued. We are also involved in a project called Trusted, which is developing a high quality sea ice buoy for surface temperature measurements. It's a cost efficient and easy to deploy design. Specifications and requirements have been defined by DMI, SHUM and NK. The prototype has now been developed and it's undergoing testing and calval activities in color calibration rooms at SHUM and DMI. Here you can see the design. It's a pole with 16 thermistors, each separated each with 3 centimeter separation. And the idea is then that this pole will be put on the ice, partly buried into the snow, so that some thermistors are in the snow and some are in the air. And then the skin temperature can be estimated from analysis of all the thermistors. And here's also an example of calibration activity where you see the spread of the different thermistors before they get calibrated, just to illustrate how important calibration is. So we look forward for this project to progress and provide some in-field data next year. And now some examples of how our climate data are used. We have contributed to the European State of the Climate with climate indicators for ice and sea surface temperature for the regions above the Arctic Circle, both the mean, and here you see the mean temperature anomaly for 2023 and the trend. In black line the average for the 30 years period, and periods with the red is then warmer than average and blue is cooler. So here you can see the geographical distribution of the surface temperature anomaly for 2023, and we see now that especially the winter months and the autumn months have large areas in the inner Arctic and along the ice edge with warmer than average temperatures. But we also see some regions where along the ice edge, especially where the temperature has been cooler, and this coincide with regions and times where the ice extent has been larger than normal along the ice edge. More results are available in the European State of the Climate Report on this URL. So that's finished my talk. Just to summarize, I've shown you some of our IST activities, including cloud masking, algorithm development, and validation of IST, and also the use of our climate data for climate indicators. Thank you for your attention.